All right, so let's take a look at the last topic for today, which was second-order differential equations. Now, second-order differential equations, as you can imagine, are going to have a second derivative in them. So we might see them written, and these aren't necessarily coupled. These are not coupled differential equations. This is one differential equation that has a second derivative in there. So we notice that this is a second derivative, all right? And we know x dot with a single dot means the derivative of x, so x with two dots is the second derivative of x with respect to time. Now, let's take a look at an example problem here. The company's pricing policy is given by the following differential equation. All right. So the second derivative of the price with respect to time plus 5 times the derivative of the price plus ATP equals 117. Okay, given that t equals 0, the price is $10 and the rate of change, let me underline this, of price is $1. Let's use Euler's method to find the long-term stable price for the product. Ooh, I love it. Now remember, rate of change is a derivative. So in other words, dp dt is a rate of change. All right, so we are given that dp dt equals 1. This is an initial condition. And p equals 10 at t equals 0. Alrighty, so then let's set this up. Erase that. Now the way that we are going to use Euler's method in this is by first substituting, oops, I write that down, let y equal, we're going to substitute dp dt for y. All right, so let y equal dp dt. So then let me just rewrite our equation. If we have the second derivative plus 5 times the first derivative okay, then that means this is plus 5y. This then is the derivative of y. If it's the second derivative, then we're going to take the derivative of y because y was the first derivative. So we have dy dt. Aha. And, oh, I'm sorry, was it plus 18p? Yeah, plus 18p. All right, so now let's just solve for dy dt. Meaning our second derivative. So dy dt in this case is going to equal 117 minus 5y minus 18p, right? Minus 5y minus 18p. Okay, now we can't solve this exactly, so we've got to use Euler's method. And so what we're going to use when we're using Euler's method here is that same old one that we already knew. We know that y sub n plus 1, oops, so the next price, sorry, the next rate of change of the price, y sub n plus 1 is going to equal the previous rate of change plus our step value, I'll just say h to say generally, times this derivative rule. All right, 117 minus 5 y sub n minus 1, the previous y value, minus 18 p sub n minus 1, the previous price. Now, the thing is, we are asked to find the long-term stable price. Remember, y is actually the rate of change of the price. So we actually need to find p, the p-values. And so how will we find future p-values? Well, just think about it. P is really the only variable in this equation. Our price, our next price, is going to be the current price, oops, plus our step size, sorry, I'm trying to catch up with myself here. My brain goes a lot faster than my mouth or my hands. All right, so current price plus our step size, so that increment times the rate of change, right? Because if the rate of change, I'm not even going to try explaining that in words. P times the, P, the current price. So let me write that out in words. Our future price, all right, is going to equal our current price plus some increment of the slope, some increment of the rate of change, current rate of change. And so now, let's find out what happens. Let's use our spreadsheet to find out what that steady price is, that stable price. Where am I? Here. Sorry. So we have T, we have Y, and we have P. I should have said P and Y. P. Doesn't matter. Really doesn't matter because they both depend on each other. Okay, at time 0, what did we have? P was 10 and Y was 1. P was 10, Y is 1. We weren't given increments. I'm just going to use 0.1 to make it a little bit easier. Drag this down. All right, and so I'm going to use this formula that we had just set up. So this is going to equal our previous price plus our increment times our rate of change in the price. All right, and so this is going to equal regular old Euler's method. This previous value plus our increment times the rule, which we calculated by hand. And so that's 117 minus 5y minus 18p. 117 minus 5y minus 5 times y. Oops, I forgot my multiplication symbol here. Minus 5y minus 18p. Minus 18 times p. What happened? Minus 18 times previous p-value. Boom. All right. Ooh, look at that rate of change. Okay, let me drag these down and let's see what happens. Uh-oh. Hang on. That's not actually an uh-oh because, hey, remember, these prices depend on the rate of change, and if I haven't filled in any rates of change, well then, they're all going to stay the same. Ooh, look at that. Okay, let me just drag this down, and let's find out if there's a stable price, right? If there's like some p-value that it approaches, and I think you can see it. Look at that, 6.5. Oop, 6.49, whoops, I forgot. It depends. It depends on the rate of change of the price. There we go. And look at how our rate of change is approaching 0. All right, so it's going to stop changing after a certain amount of time. And look, we're approaching, that's it, 6.5. That is our stable, steady price. You guys, this is such cool stuff. I hope you appreciate this. Actually, you know, if I drag this down, because look, it kind of changed a little bit. Let's just make sure it's not changing anymore. Yeah, no. Yep. Yeah, it's just going back and forth between 6.49 and 6.5. That's it. All right. Okay, so let's just start off another example that is not in the context of a word problem, and it's actually a little bit more complicated when it's not in the context of a word problem. So look, it's actually giving you a hint here in this problem by writing each as a coupled first order differential equation. Solve these. Okay, so I'll do A. D squared, sorry, let me write this here. So the second derivative of x with respect to t minus 3 times the first derivative of x with respect to t Okay, so I'm going to do the same thing I did last time. I'm going to let the first derivative, give the first derivative a different name. So I'm going to let y equal dx dt. That means later I can take dy dt, and that's going to give me the second derivative. So doing what I just said, the second derivative is going to then be the derivative of y. So dy dt minus 3y plus 2x equals 0. That gives us dy dt equals 3y minus 2x. And then, what else do we have? Well, we've got the dx dt equals y. This is our coupled first-order differential equations. We don't see any second derivatives in here. And this we can solve just like we did on Monday by setting up a matrix here. So remember, dy dt, that's the same as saying y dot. Dx dt, that's the same as saying x dot. And just to be complicated, I'm going to turn this matrix around. All right, and so we'll just say y dot x dot equals, we're going to have 3 minus 2, 1, 0 times yx, right? yx. And then you can find the eigenvalues, eigenvectors, substitute them into the equation, and you will find x, even though you were given a second order differential equation. You can do the same for problem B. And then on problem C, you don't really have to do problem C. But if you want to impress me, go ahead and do that. All right, so this was an overview of second order differential equations. Go ahead and try them out. Your homework is exercises 12I and 12J. And on Monday, we'll go over these in more depth. We'll do some calc review, and you'll be very well prepared for your test next weekend. Okay, ta-ta.